Okay, so let me introduce you. Uh, Welcome to our, I guess, fifth Stat Cafe for this semester. And then it's my pleasure to introduce Isaac Ray. He's a fourth year PhD student. He's one of my close friends here. And then he is he is working with Dr. Sang. And then his research focus on non-parametric statistic and their application to complex data analysis. Beyond his academic achievements, Isaac has been an active leader in the Department of Statistics. He was the SGSA president last year. And when he is not immersed in research, Isaac enjoys brewing the perfect cup of tea and then exploring his passion for cooking. We are thrilled to have Isaac here today with us to share his insights and experience. Please join me in giving him a warm welcome.
Oh, thank you. I've never in my life brewed a cup of tea, so I'll get right on that to make sure that
You like coffee?
I do love coffee. I've brewed many cups of coffee. All right. So this is work that I did jointly with a collaborator at Los Alamos National Laboratory, Alexei Skurikin. So he was providing sort of the domain expertise. This is a paper really about remote sensing, but the statistics required to get the remote sensing application to work ended up being something sort of beyond what most people were going to be doing independently as a domain scientist. And just to acknowledge where the money goes, I was funded both by NSF Mathematical Division, as well as I was given access to big computers at Los Alamos to run all of these big models on. Okay. So just to signpost the talk a little bit. So I'm going to start with just talking about what the goal of the project was at the outset, because things did shift a little bit as we went on. And then I'll talk a little bit each about sort of the main components of the methodology, which starts with the actual method by which we're doing clustering, which is going to be a Bayesian non-parametric clustering algorithm. Then a little bit on deep clustering, what that is, what that means, and what people have been doing in the past. Heterogeneous transfer learning, which is sort of the mechanism by which we're able to get the results as good as we did using sort of off-the-shelf clustering methods, including these Bayesian non-parametric ones. And then putting all the different pieces together and how well that it worked in the end. So really the motivation behind this whole thing is that Los Alamos is sort of prioritizing national security, and a big part of national security is how to effectively use data in order to inform decisions about risk. That's a very high level thing. In practice, what that means is they've got a bunch of satellites up in space, and they're taking pictures of the Earth, sometimes just in RGB, oftentimes in more channels than that. For example, lots of different wavelengths of light that those cameras are able to capture. But that produces enormous quantities of data. We're talking petabytes a day, even more, really. So way too much data for any group of individuals, any organization even, to actually manually sort through, look at what is in this picture, say something about it in some intelligent way. So we have to have some automatic way in order to sort through all of these pictures. Now, a lot of applications want to use what the contents of these pictures are in some downstream application, right? So they don't want to themselves have to sort through all of these pictures, because really what they're only interested in is, say, pictures of smokestacks, right? So if you're some kind of environmental scientist and you're looking at national security from an environmental angle, you might be interested to know, are people violating climate agreements? Are they building these coal burning power plants when they promised that they were not going to? Well, that's hard to tell with boots on the ground, but if we get a picture of it from space, we can say, hey, this is a smokestack. You promised you weren't going to be building these. So there's lots of applications like these that need to have sort of labeled images from space, but that can't label them themselves. This includes urban planning, land use, climate science, national security. Lots of different people want to use these remote sensing images, but they need to know what is in the pictures first. And we don't necessarily know upfront what they're looking for, right? So maybe at first we say, oh, well, they're looking for a smokestack, but maybe they have some new smokestack design that we haven't seen before, right? So we don't want to sort of specify exactly what we want in the pictures. We want this to be sort of a more automated process where we're going to use some kind of model, statistical model, hopefully, that's going to try to sort all of these images into groups, even if we can't say upfront what those groups are. And additionally, if we're just putting stuff on our wish list, why not? Let's make it cheap computationally, because if it's cheap computationally, it's cheap money-wise. These computers are expensive. we should make it probabilistic so that we hopefully have some amount of uncertainty quantification. How much are we confident that this image is what we say it is? And we'd like the groups to have a semantic meaning, right? We don't want to group them into things like, this is a picture that's mostly red, and this is a picture that's mostly blue. That's not very interesting. We'd like whatever these labels are to be semantic in a way that a human would be able to interpret them well. So formally, we want to, given some new unlabeled remote sensing images, possibly from different satellites, possibly from different resolutions, possibly different spectra, we want it to be as broad as possible. We want to take those new data sets and then partition them into groups. We don't want to specify what those groups should be of, right? So we don't want to specify any cluster labels, and we don't want to specify even how many groups there should be. And that ends up being a bit of a challenge. Most clustering algorithms want you to at least say how many clusters there should be. We don't want to say that. And ideally, for any particular image, we'd like to get probabilities for its membership in any of the different groups that we're assigning, and not just a hard assignment. So we'd like it to be probabilistic. And for this thing to be cheap, we can't just build something from scratch for every new data set, right? Every satellite has its own little quirks. They all have slight distribution shifts. Individual sensors might have individual quirks. If we're training individual models for each one of these different setups, we're going to run out of compute. So we need this to scale both sort of well across lots and lots of images in any particular data set, and we want it to scale across lots of different data sets, each with their own different properties. So as an example, this is one particular image data set from a particular satellite. This is called the Eurosat data set. And we can see it's relatively low resolution. So these pictures, I didn't really want to blow them up anymore because they'll look very grainy. So this is lots of images. Really, you can't tell a whole lot about them. For example, this one just kind of looks dark. This one is maybe farmland. This one has some white circles in it. We need to be able to work with this, but we also want to be able to work with something that's even more high resolution, maybe has more information in it. Okay, so at the high level, what we're going to do is we're going to take a pre-trained general purpose neural network, and I'll talk about what that neural network is. We want to fine tune it on some known labeled remote sensing data set, but just one of these data sets. And then we want to take it and hopefully transfer what it learned based on this fine tuning process and its pre-training to data sets that it's never seen before. Without any training, do forward passes on those images in order to get some features, reduce the dimension of those features so that we can use distance metrics in a way that makes sense. And then we want to cluster those sort of reduced dimension features into individual groups, and whatever those features get clustered into will represent the group that the image is getting clustered into. Okay, before I talk about Bayesian nonparametrics at a high level, do we have any questions about the setup and sort of the question we're trying to answer? Great. Okay, so the clustering algorithm that we're going to use is a Bayesian nonparametric clustering algorithm. For people who have not seen Bayesian nonparametrics before, which probably is not a lot of people in this audience, but Bayesian nonparametrics is not something that's saying that there are no parameters. There are parameters in this model. It just means that we don't have a fixed number of parameters. And the reason that's important is because we don't want to specify the number of groups. If we specify the number of groups, then the number of parameters is going to be sort of lined up with however many groups that we specify. We don't want to do that because we want to learn the number of groups from the data. So in a standard Bayesian method, we have some model over parameter spaces, and that parameter space will have some fixed finite dimension. Instead, we're going to use Bayesian nonparametric methods, which define these models with parameter spaces having infinite dimensions. So sort of functional parameter spaces, you may have seen things like Dirichlet processes, Gaussian processes. We're going to be using Dirichlet processes. And the intuition behind it is that by putting distributions over the different models, sort of in model space, we are able to learn the appropriate amount of complexity in our model from the data, rather than having to specify upfront how many clusters we might want. And the reason that we want this is because it's simply more flexible than standard clustering algorithms. Probably most people have seen k-means, right? We all love and know k-means. K-means, you have to specify k. And one option is to, for example, specify lots of different k's and look at some kind of elbow plot, maybe, based on some sort of maybe inter-cluster variability, intra-cluster variability, and try to optimize the choice of k based on an elbow plot. But that's sort of not very well supported theoretically, and it will very often give you quite suboptimal results. There's also distance-based metrics, things like dbScan, HDBScan, lots of these sort of distance-based ones. But in the same way that choosing K will sort of choose the number of clusters for you, choosing your distance threshold will do the same. So whatever distance threshold you set is going to implicitly tell you how many clusters you get. Instead, we want the complexity to increase with the size of our data, right? So if we are observing more complex data, we'd like the size of the model to increase in order to try to match that. So the good news is, unlike a lot of Bayesian methods, we're able to sort of use some tricks from a field called variational inference in order to reduce the fitting speed of this. So we're not going to be doing some expensive Markov chain Monte Carlo procedure in order to fit this kind of model. We're going to use variational inference to sort of do a deterministic algorithm to get to the approximate solution very quickly. So we're not going to be giving up too much in terms of speed, despite a slightly more flexible and complicated model. So in particular, the model we're going to use is called the Dirichlet process Gaussian mixture model. This is a relatively old, sort of well-known model. Essentially, there's the Dirichlet process mixture model with a base measure. We're choosing the base measure here to be a Gaussian measure. And the idea here is that we're going to generalize the standard Gaussian mixture model, where we have a fixed number of Gaussians that we want to guess the membership of, and instead try to allow it to infer how many of these Gaussians we want to have from the data. So in practice, you would use this, some kind of maybe reversible jump MCMC. Here, instead, we're going to use variational inference with a truncation, if you think about it in the stick breaking representation. Has anyone seen Dirichlet process Gaussian mixture model? Do we like it? Okay. I won't spend too much time on it then. So the key thing is that we're assuming that all of our images, in some way, actually belong to different Gaussian distributions. And each one of those Gaussian distributions has its own separate mean, its own separate covariance matrix. And we want to infer from the data which image belongs to which Gaussian cluster, with the idea being that if two images belong to the same Gaussian distribution, those images are probably similar in some way. The reason that we choose Gaussians here is mostly just convenience. It makes the inference a lot more tractable. The math and the CAVI updates become sort of feasible. If we did a mixture of a different kind of distribution, that may not be the case. But this will be the clustering algorithm that we sort of focus on primarily, with the benefit being that we get to infer both cluster membership and cluster count from the data rather than just membership. Okay. So I want to take an aside and talk about the difference between what we're doing here in clustering versus the more standard task that's done with neural networks, which is classification. So when we talk about classification using neural networks, both the number of labels and what the label content is set up a priori, right? So there's no sort of label switching problem, and the number of different things that we're trying to infer is known upfront, right? So you've probably seen, if you've worked with neural network classifiers, they have some kind of linear head at the end, where the number of nodes in that linear head is equal to the number of classes that you'd like to divide your data into. Here, with clustering, we want to not make that assumption, and in some sense, the outputs are exchangeable, right? So cluster 1 and cluster 2, 1 and 2 don't have any intrinsic meaning. It's the entire contents of cluster 1 and the entire contents of cluster 2 that have meaning, right? So it's not saying that this is a dog or this is a cat. It's saying all of these animals are similar, and all of these animals are similar. The labels are completely exchangeable, though. That's a big problem for standard neural networks, and that's the reason why clustering with neural networks is a much bigger problem than standard classifiers. The other issue is that classification tasks are pretty much always using a substantial amount of labeled data for their training procedures. Now, this has changed a little bit in recent years. We've gotten more into, for example, masked autoencoders and some other sort of clever strategies to avoid this supervised training. But in general, classification is going to be using labeled data for training, and if nothing else, it's going to be using the labels themselves when they're doing inference. One major exception, and it's the thing that we'll be comparing the most against, is so-called zero-shot classification. Zero-shot classification is a special case where we are not going to be using labeled data for the training procedure, but we are still going to use the semantic content of the labels for the inference procedure. So typically these are based on sort of VLP models. So it's a combination of both a language model and a vision model. You jointly learn the weights in both of those two things, and then you use the language part of it to infer sort of the contents of the image from the actual text of the label itself. And then you use that in order to guide your vision inference procedure. The most popular types of these models are things like CLIP from OpenAI. But the key thing to take in mind is they are still going to be bound by the number of labels, right? That they don't get to change dynamically. And they have to know what the labels are up front. You have to tell them, I am looking for smokestacks, for example. And what that label is going to change how it does the forward pass. The other major sort of difference between clustering and classification is they don't have the same metrics. So standard metrics for classification, everyone's favorite, is simply accuracy. Did you get this image into the correct class, or did you get it into the incorrect class? Whatever percentage in total of all the images that you put into the right class, that's your accuracy. The trouble with accuracy in the classification sense is that it's really painful for clustering methods because of the label switching problem. And it becomes even more painful when you don't specify how many clusters you're allowing upfront. When you allow the number of clusters to change, the algorithm for calculating classification accuracy is actually going to heavily penalize selecting the wrong number of clusters. So if there are 10 true clusters, your model guesses that there are 11 clusters, you can never achieve sort of beyond a certain accuracy threshold, even if only one image maybe was misclassified in that 11th cluster. So you're paying a substantial performance penalty to have to use classification accuracy on a clustering method that allows you to choose the number of clusters dynamically. So the reason that we're still going to talk about accuracy, even though it's not really appropriate for clustering situations, is simply because it's the easiest way we can show as a point of comparison how this method does with zero-shot classification models. Those zero-shot classification models have that fixed number of clusters and have those labels pre-specified. So they still sort of get the advantages of accuracy, whereas we don't. But we'll show that actually, even despite this kind of slight downgrade to our model's performance in some cases, we can still do quite well. Really, the more accurate metrics for clustering are things like normalized mutual information or adjusted rand index. These are things that look at how similar objects are in the same class versus between classes. We'll talk about those too. But as far as comparing with other methods, we mostly focus on classification just because there's not really a lot out there as far as comparing clustering for this particular problem. Okay, so transfer learning is sort of in the title of the talk, and really it's the crux of why this method works. And the idea behind transfer learning is to try to improve the performance of some typically neural network-based model on some target domain by transferring the knowledge from some similar problem. So a lot of people have seen the sort of vision transformer-based neural networks that are used for image classification. You pre-train them on some humongous data set of images. Maybe it's ImageNet 21. Maybe it's a combination of that with lots of unsupervised things. But the idea is you want to pre-train this model and hopefully take that model and put it in a new place where it hasn't seen the images anymore. So, for example, if we had a neural network that was originally trained to distinguish cats and dogs, hopefully it learned some sort of features that could help it distinguish a poodle from a pug, right? So the task is a little different. And if we started feeding it poodle and pug images, bless you, if we started feeding it poodle and pug images without changing the classification head, all it's going to say is dog, 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 dog. But with just a slight little tweaking to some of the weights and biases and with a new classification head, it probably wouldn't take very long for it to learn to distinguish that's a poodle and that's a pug, right? Probably the features that it learned sort of in the model backbone for distinguishing cats and dogs are probably pretty close to what it would need to learn to separate poodles from pugs. So the idea is we're going to reduce training speed by using training that other people have already done and just tweaking them a little bit. So we're going to effectively fine-tune it on a much smaller data set with a much smaller learning rate so that we're just barely shifting the weights to sort of help us out a little bit. And really, it's mostly useful because these target problems, you know, there is a lot of these satellite image data sets, but there's not that much labeled satellite imagery. It's really expensive to do that. That's the whole premise of what we're trying to do here. So we'd like to use just a little small amount of this satellite imagery in order to sort of shift the model weights just enough to be useful for telling remote sensing images apart rather than telling, for example, cats and dogs apart. So transfer learning is actually sort of a really big area. This is effectively an example of so-called heterogeneous transfer learning. So in this sort of taxonomy that they laid out here in 2020, they sort of break it down into, you can either sort transfer learning solutions into sort of their approach or in terms of what kind of setting you're doing. For our setting, we're effectively working with heterogeneous transfer learning because the images from these different data sets have completely different distributions. And all of those distributions are not only different from each other, they're also different from the distribution of the training data that this model saw. Okay, so homogeneous transfer learning is going to use the same attributes, labels, and importantly, feature space dimension across these different domains. So my favorite example of this is if you have a model that distinguishes a red car from a blue car, and you train it on sunny images, then you feed it a bunch of pictures of red and blue cars when it's rainy, hopefully your model is still able to tell those apart. This is a homogeneous transfer learning case, right? So the attributes and the labels that it's distinguishing between are the same, and the feature space that it's using is the same dimension, right? It's still just distinguishing red cars from blue cars. Still just two different things it wants to care about. On the other hand, heterogeneous transfer learning, we're going to use different feature spaces. We're going to use different label spaces. So for example, telling apart a high versus a low density urban development picture, right? So we have these pictures from space. We could say, maybe this is some suburban plot and this is some, picture of Manhattan. And somehow we want to transfer those weights into telling this is a annual versus a semi-annual versus a permanent crop field. And those images came from a different satellite orbiting a different part of the Earth with a different sensor. The feature space has changed, the attributes have changed, the labels have changed. It's a little bit more difficult than the first scenario. And in order to account for it being a little bit more difficult, we're going to use something a little bit more advanced than your standard CNN. So traditionally, a lot of these remote sensing-based neural network models have been some kind of convolutional architecture. Convolutional architectures are great for a number of reasons. However, we need something that's going to have a lot of representation power in order to be able to perform this heterogeneous learning task. So for more details, there was actually a pretty extensive review called AITLIS. So it's kind of like Atlas, but with AI. They really love their puns in remote sensing. And essentially what they did is they did a huge benchmark of lots and lots of different model architectures with lots and lots of different image data sets, tried to transfer learn across all of them, and then looked at the performance of these. And pretty much universally, vision transformers were able to outperform all of the other different classes of model architecture. So your CNNs, your ResNets, all the sort of traditional approaches. So the way that these vision transformers work, who here has seen transformers in general? Possibly as part of a reading group, perhaps? Okay, so the idea behind these transformers is that very similar to the original transformer paper, it's all about this attention mechanism, right? So we have these transformer encoders that take these patches with embeddings, right? So the embeddings here are not like a sinusoidal embedding from the original text paper. These are slightly different sort of position embeddings that essentially tell you where in a given patch a certain pixel is. So we break up our image into patches. These are typically either 14 by 14 or 16 by 16 patches. And then within that patch, we flatten it, we assign positions to all of the pixels in the patch, and that is now our sequence. That sequence goes into a sort of relatively standard looking transformer encoder. So we do our norms, we have multi-head attention, we put in our residual layers and make sure that we're taking care of our embeddings, norm, NLP, and output. And we stack these things 12 times, 20 times, a lot of times. Yeah.
So these are colored. Typically those represented by triads of numbers. How do you handle the 3 layers?
That's a really good question. So it depends a bit on the particular architecture that you're using. So there are some that completely flatten it even across channels. There are others that are so-called channel formers, and the channel formers sort of treat the channel dimension a little bit separately. From what I recall, the architecture that we are using here, I believe, just flattens it. I'm not 100% on that, but I believe it just flattens it. That's actually sort of something that we wanted to look for as sort of a future direction. Ultimately, we ended up focusing on RGB images because that's what's available as a pre-trained model. You can't really do transfer learning if you don't have a pre-trained model to start from. However, hyperspectral imagery is another big problem. And one thing you can do is either just truncate everything outside of RGB or do some kind of projection down to RGB based on the sort of higher dimension spectra. Neither one of those are really optimal. There are some very, very recent works, like in the past 6 months or so, that have tried to do fully unlabeled training of sort of like hyperspectral compatible transformer models using these massive amounts of unlabeled hyperspectral imagery. Their performance is interesting. I don't think it's ready for showtime yet. I don't think it's quite ready for downstream applications. It's really it becomes a very hard problem. Any other questions about the transformer architecture? Okay, so really the key thing here is the self-attention mechanism, which is sort of this part here in this multi-head attention, is helping us keep track of sort of the relation of a pixel with other pixels and itself. And then the positional encodings here make sure that we're not throwing away the spatial relationship both within and across patches, right? So where you are in the image can make a difference. This is actually a major reason that transfer learning ended up being important for our work. It was not in our paper, but a paper recently before ours showed that remote sensing presents a sort of unique challenge for these pre-trained models because most pictures are taken from this perspective. Remote sensing images are all top-down. And so because of that, things like rotation, which normally would have some sort of varying component, actually becomes invariant, right? A remote sensing image, it doesn't actually matter whether or not you're facing north or east or south or west. The top-down view is actually going to be pretty much equivalent, with the very few exceptions, things like shadows. Versus standard day-to-day images, you're almost always going to see a face in this orientation. You're pretty unlikely to see a face upside down. Okay, so the specific model that we ended up going with was called the Dino V2 model. If you're wondering what Dino stands for, you'd have to look it up in the Dino V1 paper, and you'll be annoyed because it's a really, really stupid acronym. But that's my opinion. We liked this model a lot. So it's very, very general. It's transformer-based. It's essentially based on the standard vision transformer components. There's only very slight modifications to it. The main advantage to this model, though, was their so-called self-supervised training strategy. So what they did is they have lots of these different training image data sets. So not just ImageNet 21, but quite a few other ones. But they did not include remote sensing images, importantly. And what their claim is, right in the title of their paper, is that they can use this model to find robust features, so the feature vector of an image, without fine-tuning. Now, we tested this and ended up not really being true in our use case, but that's their claim. Their claim is that this model is so general because of how many parameters it has, the strength of the architecture, the strength of the self-supervised training, that we actually don't need to do any fine-tuning. We can get excellent results right out of the bat. And that seems to be at least partially true as far as standard image datasets, but at least for remote sensing datasets, we found that fine-tuning actually did make a difference. Now, people have already, at the time that we wrote this paper, the Dino V2 model was very state-of-the-art. It had just been released. Since then, people have been using it. They've shown all kinds of different applications: classification, depth sensing, image segmentation, and indeed, the features that they find do end up being very powerful. You can do a lot with the features that this model extracts. And importantly for us, it often outperformed weakly supervised or zero-shot methods, despite not actually using any label information. So this is not a like VLP combination vision language model. This is strictly a vision model. So unlike CLIP and sort of these similar vision language things, we're only using the vision domain here. And then finally, the reason that transfer learning actually mattered to us, this is the difference in UMAP projection, which I'll talk about briefly in a moment, between the Dino V2 model with no fine-tuning and the Dino V2 model with fine-tuning. So this is the optimal 31 data set. It's called that because it's got 31 classes. And when we don't do fine-tuning, you can see some of these clusters do end up being relatively well separated, right? So UMAP here, this is sort of you can think of it as a nonlinear PCA. So this is based on reducing the dimension of the feature vector, which ends up being somewhere in the 1500s down to just 2 so that we can plot it. But you can see a lot of these clusters are really not separable. If we were to feed these directly into a clustering method, it's going to say blob, 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 blob. Oh, this one's over here, this one's over here. So some of these are well separated enough that we could do something useful, but the majority of them are not. Contrast that, we transfer learn based on a slight fine tuning. So we take the ResISC 45 data set, another remote sensing data set called so because it has 45 true classes. We fine tune the Dino V2 model using that data set and use it to do the forward passes on the optimal 31 data set, same projection. Now, these are really, really well separated clusters. Despite the clusters here, right, these like semantic clusters are not the same as what the true labels were in the ResISC 45 data set. Right, so our label space has changed, our feature space has changed because these also came from a different satellite. And yet, just with a small amount of fine tuning on just another remote sensing data set, we've reduced our clustering problem now to be much easier, right? We would expect that most clustering algorithms should perform quite well putting these into groups compared to this. This is very hard to cluster, this is quite a bit easier. And we get a little bit of inside baseball here about what really this fine tuning is doing. We can see that the semantic similarity between these clusters here has some geometric meaning in this space in a way that it really doesn't over there. So for example, pictures of mountains from a top-down view versus pictures of the desert from a top-down view end up looking very similar. They mostly just look like big piles of rocks and sand, mostly rocks. We also get to see things like, for example, commercial areas and industrial areas very close together. Medium and dense residential even have some overlap. Even experts sometimes can have trouble telling apart what counts as a medium residential versus a dense residential sort of area, at least from nothing but a satellite image. We see things like freeways and overpasses right next to each other, also close to intersections, bridges. We get to see things like airport and runway are close together. That's what we would expect. That's what we would hope. Forests and meadows, again, from a top-down view, these mostly just look like big green patches, right? Really, the main difference between forest and meadow is the color of green. So they're separated, but semantically, they end up being quite similar. They have big, flat, sort of constant stances, and they're not really a lot of human development going on. So this is why transfer learning is sort of useful, and this is why fine-tuning we found ended up being quite important for the quality of our results. Okay, so here's what we ended up coming up with. So we assume that we have some fine-tuning images that have labels. In our case, we ended up choosing the ResISC 45 dataset. Again, this was based on the AITLIS work, where it essentially showed that the transfer learning performance when fine-tuning on the ResISC 45 dataset was better than most other datasets. In principle, this could be most labeled datasets. There was not tremendous amounts of performance degradation, so long as you had a sufficient number of semantic clusters to sort of do well across your other tasks. Then, once we've done the fine-tuning, and that's just a one-time sort of upfront amortized cost, we take whatever our inference images are here. So we assume for some particular data set, we maybe have n of them. This is often in the tens, hundreds, millions of thousands, huge number of inference images. We pass them through our neural network backbone, our feature extractor, and that gives us n of these d-dimensional feature vectors. So for the Dino V2 model, this was about 1,500 or so. In 1,500 dimensions, a normal distance-based clustering algorithm will fit every single time. Recursive dimensionality will kick in. The distance between these things simply doesn't have any semantic meaning. So before we can apply a clustering algorithm that uses distance, we've got to bring the dimension down. To do that, we're using a manifold projection strategy. We ended up using UMAP. This is the Uniform Manifold Approximation and Projection algorithm. We looked at a lot of these. So PacMap, UMAP, TriMap, TSNE, a lot of them. Ultimately, the performance was relatively similar. The one thing that didn't work is PCA. If you use PCA, these features are just too non-linearly related. You end up with mostly just garbage. Essentially, if you apply PCA to these things, what you end up with looks like just a big ball of white noise. And so classifiers and clustering algorithms don't do well with it. But so long as you have some amount of non-linearity capability in your manifold projection algorithm, it seems to work about the same. So we stuck with UMAP because it's easy and the code runs really fast. That brings us down to just P features, where P is a lot smaller than D. We ended up going with 2, mostly because it's really easy to plot, but also because distance in 2 dimensions is pretty easy. Most methods are able to deal with that. Then, with these much smaller dimensional features, we stick them into a clustering algorithm. We get our cluster assignments up to some k hat, which we also want to estimate. And that's the feature assignments that we use. Because we're doing a Bayesian method, we do also get, because we're doing VI, approximate probabilities for each of these different clustering memberships, but we didn't end up making use of that in this particular paper. It was something more so that collaborators wanted for their own downstream tasks. Okay, so this is a pretty flexible framework. And in fact, we found lots of different papers in the literature that essentially boiled down to these steps. So for example, people swapping out the backbone. A lot of times in the past, people have done something similar to this, but with CNNs or with ResNets. A lot of times people are doing this with PCA. A lot of times people are doing this with K-means or HDB scan. So essentially they're just swapping out the components. However, we found that pretty much all of the components that we ended up choosing with were substantially better than anything that people in the literature were doing before. So other things we can do, we can change the hyperparameters, we can completely change the model, we can do some kind of ablation. We can say, what if we don't want to do clustering? We're only interested in the quality of the manifold. That's sort of this plot that I showed you here. Or we can say, what if I do try to just do a distance-based clustering with 1500 dimensional features? Spoiler alert, it doesn't work. So we looked at a lot of different schemes, lots of different sort of components for each of these three different pieces here. But in the end, we went with the large backbone Dino V2 model. So it has about 1 billion parameters, just a little bit more than that, with a patch size of 14 by 14. And we fine-tuned it on the Resix 45 dataset. So we also tried different fine-tuning datasets. Our results pretty much lined up with what the ITLIS paper found, and Resix 45 didn't end up being sort of the best. Then we used UMAP algorithm in order to reduce the dimension from 1500 to 2. Once we have two-dimensional features, we are working in a class that distance-based methods are going to be successful in. So we feed these two-dimensional features into a Dirichlet-Proces-Gaussian mixture model algorithm, and that will give us our clustering results. So before we were going to try any remote sensing data sets where the labels were either truly unknown or at least synthetically unknown, we figured, why not CIFAR-10? Everyone's favorite little toy image testing data set. The Dino V2 authors very intentionally left CIFAR-10 out of their training data so that they could sort of give valid transfer learning performance on this data set. But keeping in mind, what the Dino V2 authors were focused on was classification. Here we are doing clustering. Good news, we do really well. Now, unfortunately, since we wrote the paper and it got published, we are actually no longer the top spot, but at the time we were the top spot, and we had just about matched the Dino V2 accuracy metrics, but with clustering. So essentially, despite our sort of feature reduction down to two dimensions, and despite not using a sort of more powerful neural network-based clustering head, we're just doing clustering with Dirichlet-Proces-Gaussian mixture model, we were still pretty much matching their accuracy up to 3 decimal places. Unfortunately, since then, someone came along and took also the Dino V2 model, but they put CLIP on top of the Dino V2 model and were able to use the semantic image from the labels. And by using the semantic images from the labels, they were able to barely beat us. So they brought it up to 0.995 instead of 0.991. Womp womp. But at least at the time that we put this out, we were very, very happy with these results. We said, wow, this is a really great method of doing clustering using deep neural networks. And I still think it is, because the other thing is that their model, the so-called Turtle is what their paper is doing, is substantially more expensive than this. Not only because of sort of their whole usage of CLIP, so they're having to do sort of these big natural language sort of processing for every different label. They're also having to do multiple forward passes per image. So if nothing else, I can be assured that our method is fast and still gives very, very competitive clustering performance. And we don't have to specify the number of clusters, and they do. Okay, so we were happy about CIFAR-10. We said, great, let's go ahead and throw this at a bunch of remote sensing data sets. Here is a bunch of remote sensing data sets. Ultimately, the contents of this table are not so important, except for the fact that these numbers are very different, right? So this is the ground sensing resolution. This essentially tells you how much physical space does a single pixel in the image represent. This one tells you how big are these images. We end up essentially just forcing all of the images down to our standard size. There are other ways to do it, but we did it because it's cheap. And how many sort of true cluster labels that people assigned to these data sets. So these numbers have a lot of variability. these numbers have a lot of variability, and some of these data sets are huge. So it's got to be fast. Okay. So just to give an idea of how different some of these images are, this is example images from a bunch of these data sets. So this is a picture of a residential neighborhood. This is a picture of industrial. Industrial what? Who knows? It's just industrial, right? So another sort of problematic thing about evaluating clustering performance on this is that in some cases we found that our model had very low accuracy because the human labelers had chosen very maybe coarse-grained labels, and our model was actually separating these things into finer categories. For example, let's see if I have it. I didn't include it. Eurosat, in particular, I believe the performance was not as good as some other models because our model was actually detecting the difference between fresh and salt water, but that is not actually a label difference in the true data set. So as far as our evaluation scheme was, it was worse, even though really we were actually finding more information than what the labelers had. The other thing is this nice residential picture. Look at how beautiful and high resolution it is. Look at how grainy this picture is of industrial, or this picture, which is river. It's just a big brown blob. This could just as well be dirt, right? The only reason that they knew it was river is because they were actually cross-referencing this with geolocation on the images, right? So it'd really be a miracle if we could pick up what this thing was in some semantic way. And as it turns out, GID in particular was our worst data set because of how low resolution these features were. In some cases, there's just not enough sort of information to give a good semantic label on just the vision component alone. But we also see some other interesting things. So this is a ground track field, right? Another thing you might notice, a lot of these images have multiple things in them, right? So optimal 31 is the one that I plotted before. And one of the true features in optimal 31 is freeway. Another one is crop field, annual versus perennial crop field. So it really, some of these images end up having multiple of these in it. And that's really where the probabilistic clustering ended up being useful for collaborators. They wanted to know, okay, if our prediction from the clustering algorithm is saying that it's got some probability in ground track field, but also some probability in freeway, although without any of these labels, it probably means this is an interesting image that a human might want to look at. Because maybe it's got both a big nuclear cooling tower and a preschool. But if the label just says preschool, we're going to miss the big nuclear cooling tower that we're interested in. Some other fun ones. I really like this one, Christmas tree farm. If you showed me this picture, I'd say, what? What do you mean Christmas tree farm? It just looks like some random trees on a field. Well, it is. Commercial. This is actually not commercial. This is a university. That's another problem we found. A lot of these images are actually mislabeled. They have like the predominant feature is another label in the data set, but that they didn't choose. This is a viaduct. Does anyone know what a viaduct is? Because to me, this looks like a freeway. Yeah. So again, lots of label space differences, lots of feature space differences. That's why it makes this sort of a difficult heterogeneous transfer learning task. Okay, so how did we do? Big table, lots of numbers. Most of these don't matter. I'll just point out Eurosat and GID, the accuracy is low. Again, this has to do with both, they have very low resolution pictures, so there's less information in them straight up. And they have, so not just that, but also some of them have very, very few true features, right? So Eurosat, I think, only had 10 true classes. So accuracy is going to suffer a lot there. That's why we also compare against normalized mutual information and adjusted RAND index. We can see that for adjusted RAND index, still it kind of suffers. Normalized mutual information, we're doing a little bit better. The main metric here is this one. This is the so-called satellite SAT ImageNet IN, so the SATN benchmark. So the SATN benchmark is sort of a multitask benchmark that consists of a bunch of different remote sensing data sets, with the goal being to have some common platform for evaluating how good these remote sensing neural networks are. So we focused on the T2, the task 2. So this is land use classification or clustering. And what we're comparing here is the harmonic mean of the accuracies versus other methods, in particular CLIP methods or some fine-tuned version of CLIP. And the good news is, with our tier 2 metric of 0.64 for the, sorry, geometric mean, not harmonic mean. With our metric of 0.64, we did actually achieve state-of-the-art performance on the Satin T2 meta benchmark task. Woo! Notably, we didn't include results here for Resist 45, the reason being the model had already seen that when we did our fine-tuning. That being said, if you include the performance on Resist 45 from doing no fine-tuning, so just the base Dino V2 model, and take the harmonic mean that way, again, geometric mean, sorry, not harmonic mean. If you take it, including the Resist 45 performance with no fine-tuning, so it hadn't seen it before, it doesn't actually change the metric at all up to 3 decimal places, so we're safe. So comparing it with other sort of state-of-the-art zero-shot classifiers, again, this is comparing accuracies, which is a little bit unfair to us because of what we're doing with inferring cluster names and counts. But despite that, we actually still kick some fairly serious butt. So really, the only major losses here, again, we don't do so well on Eurosat compared to OpenClip, and that's because it's really gaining a lot from the language component of those labels that we are not gaining from. And also the Wahoo RS19, essentially we get beat here because, again, they're using a lot of semantic information in those labels that otherwise it might make it pretty hard to tell apart from an accuracy standpoint. Okay. I'll move on from boring tables. So sensitivity to different choices in the modeling part. So we use the larger Dino V2 large instead of the smaller Dino V2B. So this is the backbone size, the number of parameters in the neural network. We did see a slight improvement in accuracy when we used the bigger model, but nothing huge. So we ended up sticking with the larger model because it was still something that we could pretty easily run locally. It's fast. We also looked at increasing the embedding dimension. We thought maybe 2 is too restrictive. We're going to lose too much information going down to just 2 dimensions for our embeddings. Ultimately, for some like very low resolution data sets like Eurosat, we were able to get marginally better performance, but across the board otherwise, we actually found that more dimensions hurt us. It also made the clustering substantially slower due to the dimension issue. If we did no fine-tuning at all, so we skipped fine-tuning, we just used the base features out of the Dino V2 model, that hurt performance pretty much across the board. So transfer learning works and fine-tuning works despite their authors' claims. We also tried fine-tuning on some other data sets. In particular, CLRS had less general labels. So instead of 45 labels, it had fewer than that, and the labels had less diversity. We found that that degraded performance across the board. So really, we do want to have a fair amount of diversity in the fine-tuning set just to make sure that it generalizes well across the domain. And whenever we switched out the manifold projection, so PacMap, TriMap, TSNE, we tried a whole bunch of these things. Ultimately, none of them had any major performance implications. We stuck with UMAP because it was the fastest implementation. The UMAP projection step took less than a second, even on the data set with hundreds of thousands of images. So in summary, we like clustering. Clustering is good. Clustering is useful for collaborators, especially if they're interested in feature discovery. So what they're interested in is, what can you find in this image data set rather than I'm looking for this thing in an image data set. We like Bayesian nonparametrics because it gave us a more flexible approach for clustering. So we didn't have to specify the number of clusters because, again, when a collaborator doesn't know what they have, it's hard for them to tell you up front how many things to look for. And we like this because it ends up being really adaptable to different domains, different downstream data sets. We tried it on not just remote sensing, but some other things. It seems to work pretty well. So in the future, we've looked at some alternative clustering. So for example, the hierarchical Dirichlet process mixture model. So we could essentially do clustering using the bag of visual words instead of the standard bag of words for text applications, but at a lower feature layer. But we don't have any preliminary results on this yet, but it seems like it should work. We just haven't been able to get it to work. More of a code issue, skill issue, if you will. We've also looked at unsupervised fine-tuning. This is something that a lot of reviewers were hung up on. It's unsupervised mostly, but the fine-tuning you do is supervised. You do have those true labels for the fine-tuning data set. We felt this is a very, very small restriction because basically any domain will have some amount of labeled images that you can kind of bootstrap off of. That being said, we did at least try briefly to do a fully unsupervised method, so even the fine-tuning being unsupervised. So can we do something truly label-free? At least for right now, it looks like no. It doesn't seem to work very well. There was a paper last year that did something very similar. So again, they did sort of these self-supervised models. They tried to do fine-tuning in an unsupervised way. They claimed their results were really good. Personally, I didn't think their results were very convincing. That's maybe a matter of opinion, though. But at least for now, we feel pretty comfortable in our assumption that there's at least some amount of labeled data that you can use to bootstrap your fine-tuning process. We've also looked at online or streaming adaptations because ultimately these images are coming in every day and it'd be nice to cluster them up front rather than stick them in a repository and do it later. This is something that's a relatively straightforward thing because forward passes for neural networks is already sort of online. UMAP is already online if you use the parametric form. And there are extensions for sort of streaming or online inference for the Dirichlet process mixture model. So relatively small tweaks there. And the last thing we were interested in, can we do manifold embedding into a non-Euclidean space? So for example, could we cluster it onto a sphere, right? Maybe with some geolocation involved in that, and then use clustering based on the sphere. So for example, there is Dirichlet process Gaussian mixture on the sphere. Again, that has a lot of implementation hurdles, but it does seem, at least preliminarily, that that is actually a promising direction as well. And that's all I have.
Probabilities of cluster labels that you get out of patient. What exactly does that look like? Just it's just pairwise probabilities. How often two images are to the same class? And like when you have a gigantic data set,
Mhm.
how do you make those comparisons? Because you can't have pairwise 100,000 by 100,000 matrix.
Yes, that's a very good question. So this has to do with a very old and storied problem with Dirichlet process mixture models, which is that how do you summarize the clustering metrics at the end when the number of clusters might have been changing as you did your inference procedure and could still change as you introduce more data. As far as the sort of pseudo probabilities that we are outputting, this is based on the final number of clusters. So this would change if we switched to that streaming adaptation for DPGMM. As long as we're doing the non-streaming version and we're doing variational inference for it, in principle, the number of clusters at the end is sort of the number of clusters that we end with. And if we added new data, we would actually start from the beginning and run the entire algorithm all over again. So those probabilities are approximate posterior probabilities for cluster membership into the number of inferred groups. So for any particular image, you would get a k-hat vector of probabilities for its probability of membership in each group. But yes, that's a major challenge for the streaming adaptation in particular, because if you allow new data to always be coming in, but you want to continue to sort of learn based on also the previous data that you've already seen, and you're allowing the number of clusters to change over time, yeah, things can get messy, especially computationally, because essentially the algorithms that I've seen for doing this require going back and sort of recalculating the probabilities every time the number of estimated clusters changes.
I'm curious, what's your hypothesis on, when you do your transfer learning fine-tuning, you're still, when you do that, you still have like hard class labels to kind of do the transfer learning.
Mm-hmm.
Do you oversee like any problems when, when people were going to be using your algorithm, basically try to connect to their data set, but it may not replicate. Maybe their data set doesn't exactly replicate the categories from the original transfer learning. Do you see any problems with that, or do you foresee that being an issue?
That's a really good question. So that's something that, yeah, we were very concerned about at the outset of the project, and that's the reason that we were so sort of reassured by this picture in particular, because the labels from Optimal 31 and the labels from Resist 45 here are quite different label spaces. So they have a little bit of overlap. Some of the labels are consistent, but some of them are sort of, if you look at like the intersection, are completely outside it, right? So it's like there are labels that Optimal 31 has that the fine-tuning data set did not, and vice versa. Despite that, the performance still seemed pretty good. We did notice that there is definitely an advantage to fine-tuning on data sets that have more diverse ground truths, at least as far as the fine-tuning procedure that we used, which was supervised. So using that sort of supervised fine-tuning procedure, it is important to have a sufficient amount of diversity in sort of the training set that you're giving it. Otherwise, we noticed a little bit, less so with CLRS, but one thing we tried very early on was a much smaller model that was CNN based with the Euroset dataset, which only has 10 true clusters as our fine-tuning dataset. We found that it did not generalize well at all. Essentially, those 10 clusters it had didn't end up sort of having enough diversity for it to have much. The model was not expressive, essentially, on more complicated data sets because of how simple the fine-tuning data set was.
I'm curious. Another models out there where you give it an image and then maybe an L, like somehow, like kind of like an LLM thing that explains what the image is inside the image. No. Simple.
Yeah, no, that is more similar to sort of these VLP, like hybrid language vision models, and they're really interesting. So they don't quite fit the bill for the particular task that our collaborators were interested in, but I will say, especially for, I mentioned sort of this like a hierarchical, like visual bag of words approach, doing segmentation using an approach like this in order to essentially break up the image and then feeding that broken up image with patches labeled by contents into something like an LLM for summarization is something that the National Lab System is very interested in. The reason that I was late to respond to her email and made lunch more difficult is I was at the conference on data analytics last week, which is put on sort of by the lab system, and the use of so-called foundation models, which are these big neural network models to do things like what you said, are a really big priority in the next few years. They're spending a lot of money on that, and they're very interested in those results.
You tried different values of P.
Different values of. Oh, yes. So we did try different values of P. So D is sort of set by the backbone. So for example, for the model we used, it was about 1500. There were sort of bigger backbones that had an even bigger D, but for the most part, since we stuck with just a few models, D is approximately fixed condition on your backbone. But we did try different values of P. So for example, I mentioned we tried in 64 instead of 2. What we found is that for the very low resolution data sets, the performance was very marginally better, but for pretty much all the other data sets, it was worse. Ultimately, there's sort of this trade-off between you want your dimension to be low enough that distance has a nice semantic meaning for your clustering algorithm to take advantage of, but you also don't want to bring it down so low that it's very hard to separate clusters in so few dimensions.
Okay. Later, we need to go.
Oh, no, it's fine. We have time.
So in the manifold position, did you supervise the unsupervised?
It's unsupervised. So we're using UMAP. It's a unsupervised clustering. It's similar. The manifold projection step itself, it's essentially like PCA. So you're not actually using any information about the response or the true label. It's just based on the features and how they are related to each other. Thank you.
Okay.